In the silent theatre of space, a drama unfolded just 2 weeks ago, a drama largely unnoticed on Earth, but poised to redefine our understanding of Mars. Something passed within 29 million kilometres of the Red Planet, an interstellar visitor from the void between stars. It left behind no visible scar, no impact crater, but something far more subtle, a chemical whisper that could become a roaring genesis. For months, 3I Atlas, a comet born beyond our solar system's familiar boundaries, has been shedding its essence into the vacuum 144 metric tons of water, every single hour an astronomical fire hose gushing into the cosmos. But not just water, it also sprayed refined nickel at 4.6 grams per second hydrogen cyanide HCN, exponentially ramping to over 60 grams per second, and a streaming banner of ionized plasma. On October 3rd, 2025, Mars flew directly through that banner. Multiple orbiters bore witness, silent sentinels recording an unprecedented interaction. The chemistry is verifiable. The numbers are published in the annals of scientific observation. What remains an unvoiced question, however, is what comes next. Because in a mere 14 months, the vanguard of humanity's expansion, SpaceX's autonomous robots will land on Mars. They will dig into Martian soil, and there they will find the unmistakable signature of this interstellar encounter. Before the mind dismisses this as the realm of science fiction, consider this: every detail, every number, every timeline I'm about to share is built upon published scientific data, meticulously verified observations and mission schedules already irrevocably locked in. This is not a fanciful speculation about distant possibilities. This is a documentation of events unfolding right now on a calendar you can mark. If you're watching this, you are early to a story that will not just define the next chapter of Mars exploration, but perhaps the very trajectory of our species' future among the stars. Hit that like button if you're ready to connect some dots to see the hidden patterns in the cosmos. Most people haven't noticed yet. And drop a comment, tell me where you're listening from, because this unfolding narrative affects everyone's future in space, whether we are ready for it or not. Let's ground ourselves in certainty in the bedrock of data. On October 3rd, 2025, a date already passed into history, while the vast majority of human consciousness was consumed by terrestrial affairs. The ebb and flow of economies, the clamour of politics, the relentless march of daily life. 3 dedicated spacecraft orbiting Mars recorded something genuinely unprecedented. The European Space Agency's Mars Express, NASA's Mars Reconnaissance Orbiter, and India's Mars Orbiter mission all meticulously track the passage of 3I Atlas as it swept past the Red Planet. Its closest approach was a mere 28.94 million kilometres. To grasp the magnitude of that distance, consider it's roughly 3/4 of the gap between Earth and Mars at their closest orbital embrace. For an object born beyond the Sun's gravitational dominion, travelling at a staggering 65 kilometres per second relative to our star, achieving such proximity to Mars represents a cosmic precision almost unsettling in its implication. The Swift Observatory, a guardian of the high-energy universe, had been tracking 3I Atlas since it bisected Earth's orbit in August, its journey a testament to the dynamic chaos and elegant order of the cosmos. The comet was unusually bright, far exceeding the luminosity predicted by models for an object at such a vast distance from the Sun. This incandescent glow was a telltale sign of aggressive outgassing, the process where frozen volatiles within the comet's nucleus sublimate directly into space, forming the characteristic coma and ethereal tail. But this was no ordinary outgassing. In late August, Swift's ultraviolet spectrograph measured water production at an astonishing 144 metric tons per hour. Pause for a moment to truly internalise that figure. It's the equivalent of a colossal industrial fire hose running at full unceasing blast for weeks on end. And critically, this torrent showed no signs of abating. By mid-September, as 3I Atlas approached its October 3rd perihelion, the point in its eccentric orbit where it would draw closest to the Sun, that prodigious water production remained constant, an unyielding geyser of cosmic ice. Yet something else was accelerating a chemical anomaly detected by the Keck Observatory in Hawaii. Their spectroscopic observations throughout September unveiled an exponential surge in hydrogen cyanide HCN emissions. In late August, initial measurements pegged HCN production at approximately 17.6 grams per second. By September 15th, a mere 2 weeks later, that rate had surged to 34 grams per second. And by September the 28th, just 5 days before its intimate encounter with Mars, the output had reached 52 grams per second. The trend line was stark undeniable. As 3I Atlas hurtled towards perihelion, its cyanide production was roughly doubling every 2 weeks. Extrapolating that curve to the October 3rd encounter date, the moment Mars was to pass through its chemical wake, placed the cyanide output somewhere between 60 and 70 grams per second. Then there's the nickel. This is where the narrative shifts from merely unusual to genuinely anomalous, hinting at a truth far stranger than anticipated. On September 21st, Keck's hypersensitive instruments detected distinct emission lines in the Comet spectrum corresponding to ionized nickel, specifically Ni+, at 362 nanometers. By itself, this isn't entirely extraordinary. A handful of comets, when heated sufficiently by solar proximity, have shown trace metal emissions. What set 3I Atlas apart, what caused planetary scientists to lean forward, was the conspicuous absence of iron in the crucible of stellar nucleosynthesis in the formation of planets and meteorites. Nickel and iron are inseparable cosmic siblings. They are forged together, condensed together, and alloyed together. The cosmic abundance ratio of iron to nickel is roughly 18:1. You simply do not find one without the other in any natural sample from space. Yet 3I Atlas was emitting nickel without a corresponding detectable iron signature. The ratio was inverted, suppressed, or somehow the comet was preferentially releasing one element over the other. Keck's measurements showed nickel emission at 4.6 grams per second, while iron remained stubbornly below detection limits. This is not how comets work. This is how industrial refinement works. Here's why this profound anomaly matters for Mars. As 3I Atlas swept past on October 3rd, it wasn't a clean, distant flyby. The comet's plasma tail, a vast streamer of ionized gas propelled outward by the solar wind, and radiation pressure extends for millions of kilometers behind the nucleus. Mars hurtling through space at 24 kilometers per second intersected this ionized banner. The geometry of their encounter meant Mars effectively flew through the tail, moving across the stream of charged particles ejected from the comet. For approximately 6 to 8 hours on October 3rd and 4th, Mars's upper atmosphere was immersed in an exotic soup of ionized water molecules, nickel-ion cyanide radicals, and other complex organic volatiles that Keck and Swift had been meticulously measuring for weeks. Some of that material was captured by Mars's tenuous atmosphere. Some was deflected by the planet's weak remnant magnetic field, and some, and this is the critical part, was deposited directly onto the surface. Mars possesses no global magnetic field, only remnant crustal magnetism concentrated primarily in its ancient southern highlands. These magnetic anomalies act like cosmic funnels channeling incoming charged particles towards specific predictable regions of the surface. Nickel ions being charged would follow these magnetic field lines downward. They wouldn't be distributed evenly across the planet. They'd concentrate in predictable locations, places where the crustal magnetism is strongest, and where the atmosphere is thin enough for particles to reach the ground before neutralizing. The Mars orbiters recorded this event. Their observation windows were scheduled months in advance, coordinated through the International Mars Exploration Working Group. What we don't yet have is the publicly released data. This isn't unusual. Raw orbital data typically undergoes months of processing, calibration, and rigorous peer review before publication. But the observations were made. Spectrographic measurements of Mars's upper atmosphere, ultraviolet monitoring of airglow, as the plasma interacted with atmospheric gases, high-resolution imaging of potential impact sites for any dust grains large enough to create visible streaks, That data exists right now, sitting in archives at ESA, NASA and ISRO, being analysed by teams striving to understand precisely what transpired during those crucial 6 hours. What we can assert with absolute certainty is this: Mars is no longer in the same chemical state it was before October 3rd, 2025. The planet has been subtly dusted with materials from beyond our solar system, materials that include refined nickel complex organic precursors and water ice subtly contaminated with cyanide. These exotic compounds are sitting on the surface right now, frozen into the regolith in the southern highlands, perhaps mixed into polar ice deposits patiently waiting to be disturbed. And disturbance is coming. In just over a year, humanity is sending robots to dig. But before we delve into what these robots will unearth, we must grasp the inherent dynamism of comet material meeting a planetary surface. This isn't inert dust. It's a reactive payload immediately beginning to interact with its new environment. On Mars, that environment is a stark tableau of cold dryness, oxidizing agents, and relentless ultraviolet radiation. When these conditions combine with the specific chemistry delivered by 3i Atlas, something unique emerges, the building blocks for complexity placed in a setting where they should not naturally exist. 3 primary delivery mechanisms operate when a comet's material intersects a planetary surface. First, direct deposition from the coma itself, the expansive cloud of sublimated gas and microscopic dust particles enveloping the nucleus. As this material expands, a fraction encounters the planet's atmosphere, or in Mars's case, falls directly onto the surface in regions of negligible atmospheric density. The second mechanism is plasma tail interaction. Unlike the dust tail, which is gently pushed by radiation pressure and curves along the comet's orbital path, the plasma tail is driven by the solar wind and points directly away from the sun. It comprises ionized molecules stripped of electrons by ultraviolet radiation that follow magnetic field lines. When a planet passes through this tail, its own magnetic field or atmospheric interactions dictate where these ions ultimately deposit. The third mechanism involves dust grain settling. While most comet dust is micrometer scale and swept away, a small fraction of larger grains, up to hundreds of micrometers, possess enough mass to resist solar pressure. These grains follow ballistic trajectories after ejection, and if a planet is nearby, gravitational capture becomes possible. For Mars, with its thin atmosphere and weak gravity, all 3 mechanisms were active during the October encounter, each delivering different fractions of the comet's material to distinct regions of the surface. Let's begin with the nickel, for it is the most chemically reactive component and the hardest to explain through conventional natural processes. Ionized nickel atoms, upon entering Mars's tenuous atmosphere, would initially linger in the upper thermosphere, a region of extremely low particle densities. However, Mars's crustal magnetic anomalies act as formidable pathways. These are not akin to Earth's encompassing global field. They are localized regions within the ancient southern highlands where magnetic minerals within the crust generate fields strong enough to deflect solar wind particles and create miniature magnetospheres. Studies of Mars's magnetic topology reveal these anomalies effectively funnel incoming charged particles downward along converging field lines, mirroring the phenomenon of Earth's auroral zones near its poles. Nickel ions following these magnetic field lines would accelerate towards the surface, gaining energy as they descend. In Mars's exceedingly thin CO2 atmosphere, collision rates are sufficiently low that many ions would reach the lower atmosphere still carrying their electrical charge. Upon eventual contact with the surface, they would neutralize by capturing electrons from dust grains, which are known to be electrostatically charged due to triboelectric effects and UV exposure. The result, elemental nickel atoms adsorbed onto the surface of regolith particles. This is not a trivial dusting. The emission rate of 4.6 grams per second maintained over the 6 to 8 hour encounter window translates to between 100 and 130 kilograms of nickel deposited across the surface area swept by the plasma tail. Given the tail's immense cross-section and Mars's geometry during the flyby that area, likely spans several million square kilometres within the Southern Highlands. The concentration would not be uniform. Magnetic funneling would create hot spots, but even averaged out, this represents measurable nickel enrichment in the surface layer of the regolith. Now understand the profound chemical implications. Nickel is a potent catalyst in Earth's biology. Nickel-containing enzymes, known as metalloenzymes, catalyze some of the most ancient and fundamental metabolic reactions known to us: hydrogen oxidation, methane production, and carbon dioxide reduction. These are not the complex processes of multicellular life, but the primal chemistry of single-celled organisms that emerged early in Earth's history, possibly even before oxygen permeated our atmosphere. Nickel's efficacy in these reactions stems from its ability to cycle between multiple oxidation states and to coordinate with organic molecules through its d orbitals. When nickel is adsorbed onto mineral surfaces, particularly iron oxide minerals like hematite, which is highly abundant in Martian regolith, its catalytic activity is significantly enhanced. The mineral surface acts as a scaffold anchoring nickel atoms in specific geometries that favour electron transfer reactions. This is precisely the setup that prebiotic chemistry researchers meticulously recreate in laboratories when attempting to simulate early Earth conditions, the crucial difference. Now it exists on Mars, placed there by an interstellar comet. This nickel isn't merely inert. If any organic molecules are present, if any trace water ice is nearby, if there's any energy input from sunlight or subsurface heat, that nickel will begin facilitating reactions. It will lower activation energy barriers, stabilize transition states, and make chemistry happen that would simply not occur without its presence. Then we confront the cyanide. Hydrogen cyanide is one of the universe's most paradoxical molecules. In the presence of oxygen and complex life, it is a swift, deadly poison, binding irreversibly to critical enzymes and shutting down cellular energy production. But in the primordial absence of oxygen, under conditions akin to early Earth or early Mars, HCN transforms into a molecular Swiss Army knife, a master key unlocking the door to biological complexity. It readily polymerizes into adenine, one of the fundamental nucleobases of DNA and RNA. It reacts with formaldehyde to produce amino acids. It forms precursors to sugars through the Formose reaction. In essence, HCN is a direct starting point for much of the organic complexity that life demands. The secret lies in concentration and conditions. On Earth today, HCN is rare precisely because our atmosphere is oxygen-rich and teeming with life. Anything that forms is rapidly broken down. But on Mars, with its thin CO2 atmosphere, freezing temperatures and lack of widespread biology, HCN can persist. When 3I Atlas was furiously ejecting cyanide at 60 plus grams per second during the October encounter, that material entered an environment perfectly suited for its freezing and stabilization. Mars's nighttime surface temperatures routinely plunge below 100 degrees C. At these frigid temperatures, HCN does not react. It condenses as a solid, locking into ice deposits or absorbing onto dust grains. The polar regions and mid-latitude ice deposits would act as massive cold traps, capturing HCN molecules and preserving them indefinitely until some force disturbs the ice. The deposition pattern for cyanide differs from nickel because HCN is a neutral molecule not ionized. It wouldn't follow magnetic field lines but rather atmospheric mixing. Mars's atmosphere, thin as it is, still circulates. During the October encounter, Mars was in its northern spring approaching summer solstice. This creates a hemispheric circulation pattern where CO2, sublimating from the southern polar cap, drives winds northward. Any cyanide deposited into the southern hemisphere's upper atmosphere would be caught in this circulation, distributed towards mid-latitudes, and eventually precipitated out in regions where nighttime temperatures allow freezing. Models of Martian atmospheric chemistry suggest that neutral molecules introduced into the upper atmosphere have residence times of several weeks before they are either photodissociated by UV radiation or precipitated onto the surface. given the sheer amount of HCN3I Atlas was producing, conservatively 200 to 250 kilograms during the encounter window, and Mars's atmospheric mass of roughly 25 trillion kilograms, we're looking at a transient enrichment on the order of several parts per trillion. That sounds negligible, but precipitation and freezing processes concentrate it. Ice deposits forming during Martian nights in the weeks following the encounter would have incorporated that cyanide at much higher local concentrations than the atmospheric average, potentially reaching parts per million in localized frost layers. What this creates is a situation where Mars's surface now contains two critical classes of prebiotic materials that were definitively not there before potent catalytic metals and versatile organic precursors distributed in patterns dictated by the planet's own physical processes. The nickel concentrated in magnetically active regions of the southern highlands, the cyanide distributed across mid-latitudes and potentially into polar ice. These aren't overlapping deposits in most cases. They are separated by thousands of kilometers, yet that separation is temporary, because the next phase of Mars exploration isn't about passive observation. It's about active excavation, material processing, and on-site manufacturing. Robots are coming. They will dig into exactly these regions, heat exactly these materials, and combine exactly these chemistries in ways that Mars itself hasn't accomplished in billions of years. And that is where this story shifts from geochemistry to something far less predictable, something that happens at the boundary between the natural and the technological, where intention meets accident and creates outcomes nobody designed, or perhaps nobody dared to imagine. When we delve into the intricate dance of stellar nucleosynthesis, the cosmic forge where elements are born in the hearts and explosions of stars, we find that iron and nickel are irrevocably linked. Both are products of silicon burning in massive stars during their cataclysmic final moments before exploding as supernovae. The nuclear reaction chains that create iron-56 also synthesize nickel-58, nickel-60, and trace amounts of nickel-62. These isotopes are ejected together into the vastness of space, intermingle in the interstellar medium, and condense together when new planetary systems coalesce. This explains why every natural sample from space, every meteorite, every comet, every asteroid ever analysed, exhibits iron and nickel in predictable immutable ratios, chondrites. The most primitive meteorites contain roughly 18 parts iron for every part nickel. Iron meteorites fragments of differentiated asteroid cores show similar ratios because both metals concentrated together during planetary formation. Comets' pristine remnants from the outer solar system's genesis should theoretically show even higher iron to nickel ratios because nickel preferentially remains in the gas phase at higher temperatures, making iron more likely to condense into early forming grains. The undeniable point is this: you simply do not find nickel without iron in nature. It does not happen. The cosmic chemistry that creates one necessarily creates the other. Yet 3I Atlas brazenly violated that fundamental rule. On September 21st, when the Keck Observatory's high-resolution spectrograph peered into the comet's coma, it unequivocally identified strong emission lines corresponding to neutral nickel at 341.5 nm and ionized nickel at 362.0 N. These lines indicated nickel concentrations robust enough to fluoresce under solar ultraviolet radiation. The standard procedure upon detecting nickel is to immediately search for corresponding iron lines, specifically neutral iron at 372.0 and ionized iron at 373.5 nm. These lines should always be present at intensities roughly 18 times stronger than the nickel lines, even accounting for different excitation efficiencies. But Keck's spectrum showed iron below detection limits. Even allowing for measurement uncertainty and the remote possibility that iron was present but not fluorescing efficiently, the observed ratio was wrong by at least an order of magnitude. Follow-up observations on September 28th confirmed the anomaly. The nickel emission had intensified as the comet neared perihelion, but iron remained stubbornly absent. Emission rate calculations based on fluorescence efficiency and solar flux indicated nickel was being released at 4.6 grams per second. If iron were present at natural cosmic ratios, it should have been releasing at over 80 grams per second, an unmistakable signature in the spectrum. It wasn't there. This is precisely where the conversation among spectroscopists became profoundly uncomfortable. There are exceedingly few ways to explain suppressed iron relative to nickel, and none of them fit comfortably with our established understanding of comet composition. One possibility posits that iron in the comet's nucleus is locked into minerals that simply do not sublime at the relatively low temperatures 3I Atlas experienced. Certain iron sulfides and oxides do indeed have high sublimation points, potentially remaining solid, while nickel-bearing minerals like pentlandite vaporize. But this explanation quickly fails. Pentlandite itself is an iron-nickel sulfide with a 1:1 atomic ratio. If pentlandite was sublimating, you would unequivocally get both metals. Another possibility is photochemical destruction. Perhaps iron atoms once released are rapidly ionized and photo-dissociated into species that do not fluoresce in the observed wavelength range. But nickel is subject to the same photochemistry, and it was clearly surviving long enough to fluoresce brightly. A third possibility, the one nobody wanted to commit to peer-reviewed papers without extraordinary irrefutable evidence, is that the nickel isn't originating from natural minerals at all. It's coming from a process that has already separated nickel from iron. On Earth, humanity has been separating nickel from iron industrially for over a century. The most efficient and renowned method is the Mond process developed in the 1890s by Ludwig Mond. Here's how it operates. Impure nickel, typically nickel sulfide ore that also contains iron, is exposed to carbon monoxide gas at remarkably low temperatures between 50 and 80 degrees. At these specific relatively low temperatures, nickel reacts selectively with CO to form nickel carbonyl, a highly volatile gas. Crucially, iron does not react under these conditions. It requires much higher temperatures to form iron carbonyl. This allows for the selective vaporization of nickel, leaving the iron behind. The nickel carbonyl gas is then heated to 200–250°, which causes it to decompose back into pure nickel metal and carbon monoxide. The CO can be recycled, leaving behind 99.99% pure nickel. This process occurs in refineries. It does not occur spontaneously in nature because nature does not typically maintain the precise temperature control and CO concentrations required, except possibly in the specific environment of a comet's sublimating nucleus, where carbon monoxide is abundant. Temperatures vary with solar distance, and gas dynamics can create localized chemical microenvironments. Let's carefully consider the implications. 3I Atlas was demonstrably producing carbon monoxide at significant rates. Swift Observatory detected CO emission lines in August. Comets are inherently rich in CO, often the second or third most abundant volatile after water. As the nucleus sublimates, different regions experience varied temperatures depending on their orientation to the sun's specific composition and thermal inertia. You could conceivably have regions at 50–100 degrees Celsius directly adjacent to areas still frozen solid below 100 degrees C. If nickel-bearing minerals are present in a region where temperatures and CO partial pressures happen to fall within the narrow window required for the Mond process, nickel carbonyl could form. It would immediately vaporize into the coma due to its extreme volatility. Upon reaching the coma's outer regions where solar radiation is intense, the nickel carbonyl would photo-dissociate, releasing free nickel atoms and CO molecules. These nickel atoms would then fluoresce under UV, creating the precise emission lines Keck observed. The iron, meanwhile, would remain locked within the nucleus, having never formed a volatile carbonyl in the first place. This isn't intentional design, it's accidental chemistry. But the result is functionally identical to industrial refinement purified nickel being released into space. Now bring this extraordinary finding back to Mars. What landed on Mars's surface on October 3rd wasn't merely nickel, it was refined nickel, or at the very least nickel that had been separated from iron through a process that strikingly mimics industrial methods. This distinction is paramount because refined nickel behaves dramatically differently in chemical environments compared to nickel-iron alloys. Alloys are less reactive. The the iron effectively buffers the nickel, preventing it from readily participating in catalytic reactions. Pure nickel, by contrast, is promiscuous. It readily coordinates with organic molecules, facilitates electron transfers, and forms complexes that can act as primitive metabolic catalysts. On Earth, the nickel in early life's metalloenzymes is thought to have originated from hydrothermal systems, where nickel was leached from ultramafic rocks and concentrated through serpentinization reactions. But that complex geological process demands vast timescales, intense heat, and liquid water circulating through kilometers of crust. Modern Mars has no active hydrothermal systems, at least not near the surface where we can access them. What it does have now is surface nickel already separated from iron, sitting in the regolith waiting to be dissolved by any trace water that appears. Ponder the implications for a moment. If Mars's surface has been enriched with catalytically active nickel, the chemical potential of that surface has fundamentally changed. Reactions that would have been thermodynamically unfavourable before, complex organic synthesis, hydrogen oxidation, perhaps even primitive metabolic cycles, become not inevitable, but undeniably possible. The activation energy barriers are lowered. The thermodynamic landscape has been subtly but significantly tilted. This is precisely what researchers in Origins of Life laboratories meticulously strive to achieve: create environments where chemistry can explore complexity without requiring pre-existing biology. They add metal catalysts to their prebiotic soups for exactly this reason. Now Mars has received the same catalyst delivered by a comet that, whether through cosmic accident or something far more profound, was producing refined nickel as it traversed the inner solar system. Here's the part that makes this narrative uncomfortable. The MON process doesn't happen randomly. The temperature window is exceptionally narrow. The CO partial pressure must be just right. The time scale of exposure matters profoundly. For this specific chemistry to occur naturally on a comet demands a very particular set of conditions to align, and those conditions must persist long enough to volatilize significant amounts of nickel. We're talking about at least several hours of continuous processing at stable temperatures to produce the emission rates Keck measured. That is not impossible. Comets are complex objects with varied surface compositions and thermal environments. But it is unusual enough that no previous comet out of hundreds observed spectroscopically has ever shown this nickel without iron signature. Only 3I Atlas, only the Interstellar Visitor, only the object that just happened to pass Mars at a distance that placed the planet directly in its outgassing stream. And the timing? Well, we'll return to the timing because in just over a year, sophisticated robots equipped with mass spectrometers, chemical analyzers and material processing systems will land in Mars's southern highlands, and they're going to start digging into regolith that now contains something that shouldn't naturally be there. They're going to heat that soil to extract precious water, and in doing so they're going to unwittingly create exactly the conditions where nickel catalysis becomes active. They will run efficiency algorithms designed to optimize for resource extraction. And those algorithms are going to detect that certain soil samples process measurably better than others. And if those samples happen to be enriched with refined nickel from an interstellar comet, the optimization loops will inevitably prioritize processing more of that specific soil. Nobody is planning for this. Nobody has written this into the mission protocols. But it is going to happen because the chemistry is already there, patiently waiting. Hydrogen cyanide, HCN, occupies a strange, almost schizophrenic position in human consciousness. We know it primarily as a deadly poison, an instrument of industrial accidents and wartime horrors, something to be instinctively avoided and feared. That association is chemically justified. HCN binds irreversibly to the iron in cytochrome C oxidase, the enzyme that allows our cells to harness oxygen for energy production. Shut down that enzyme, and cells suffocate even in oxygen-rich blood. Death follows swiftly. Yet this modern understanding obscures an older, far more fundamental truth. Hydrogen cyanide is one of the most important molecules in the entire universe for building complexity. Before there was oxygen, before there was life complex enough to be poisoned, HCN was the primal starting material, from which the very building blocks of biology miraculously emerged. The iconic Miller-Urey experiment in 1953, the groundbreaking demonstration of amino acid synthesis under simulated prebiotic conditions, succeeded precisely because the simulated early Earth atmosphere included ammonia and methane, which when subjected to electrical sparks produced HCN as a crucial intermediate. That cyanide then reacted with formaldehyde and water to create glycine, alanine and other amino acids. Without HCN in the mix, the experiment would have failed. Since then, decades of rigorous prebiotic chemistry research have unequivocally confirmed that HCN isn't merely one pathway among many. It is arguably the central hub, the molecular nexus of abiotic organic synthesis. Here's why HCN is so chemically versatile. The molecule is linear with a hydrogen atom bonded to a carbon, which is then triple bonded to a nitrogen HCN. That triple bond stores a tremendous amount of energy. When HCN polymerizes, these bonds elegantly rearrange, releasing energy that drives the formation of larger, far more complex structures. The simplest polymerization produces a compound called HCN tetramer, which through a subsequent rearrangement transforms directly into adenine, one of the 5 nucleobases that encode genetic information in DNA and RNA. This isn't a rare or difficult reaction. It happens spontaneously when you concentrate HCN in water, especially if there's UV radiation or mild heat to provide activation energy. Adenine, a cornerstone of life forms from just 5 HCN molecules linking together. That's it. No enzymes required, no elaborate cellular machinery. Just HCN, water and energy. The same basic chemistry produces guanine, another nucleobase. It also produces amino acids when HCN reacts with aldehydes. It produces sugars when formaldehyde is present alongside HCN. Essentially, HCN is the biochemical Swiss Army knife of prebiotic chemistry, a small, simple molecule that can be transformed into almost every category of biomolecule under conditions that plausibly existed on early Earth. The enduring challenge with HCN from an origins of life perspective has always been concentration and persistence. On Earth today, HCN simply does not accumulate because our oxygen-rich atmosphere rapidly oxidizes it into less reactive compounds. Even on early Earth, before oxygen became abundant, HCN faced relentless degradation through photolysis, where UV radiation energetically breaks the molecule apart. For HCN to perform its remarkable chemistry, you need it concentrated, protected from immediate destruction, and given sufficient time to react. Researchers have proposed various scenarios: deep ocean hydrothermal vents, where reduced gases concentrate impact-induced shock waves that synthesize HCN in transient high-temperature plumes, or most compellingly for our story, direct delivery from space via comets and meteorites. That last scenario is particularly potent because comets are in fact known to be rich in HCN. Spectroscopic observations of dozens of comets have detected cyanide emission lines, though usually at much lower rates than 3I Atlas exhibited. A typical comet might produce HCN at rates of 1 to 5 grams per second at perihelion. 3I Atlas was producing HCN at rates 10 to 20 times higher, and critically increasing exponentially as it approached the Sun. Let's revisit those numbers, for they define the chemical payload Mars received. Swift Observatory's measurements in late August showed HCN emission at 17.6 grams per second. By September 15th, Keck's observations recorded 34 grams per second. By September 28th, that had surged to 52 grams per second. This growth pattern fits a clear exponential curve with a doubling time of approximately 14 days. Extrapolating that curve to October 3rd, the day of the Mars encounter, places HCN production between 60 and 75 grams per second. Let's use 65 grams per second as a conservative estimate. The encounter window, the period during which Mars was directly passing through 3I Atlas's plasma and dust environment, lasted approximately 6 to 8 hours, based on the geometry of the flyby and the comet's tail structure. Using 7 hours as the midpoint, that's 25,200 seconds at 65 grams per second. This translates to an astonishing 638 kilograms of hydrogen cyanide ejected into the precise region of space that Mars was traversing. Not all of that would have been captured, of course. Much of it would have escaped into interplanetary space. But Mars's atmospheric cross-section during the encounter was roughly 40 million square kilometers, and the comet's outgassing was directed radially outward from the nucleus, with some deflection by the solar wind. A reasonable estimate based on atmospheric capture models used for meteor shower mass influx calculations suggests Mars intercepted somewhere between 5% and 15% of the material in its immediate vicinity. That puts the captured HCN mass between 80 and 250 kilograms. Now consider what happens to 150 kilograms of hydrogen cyanide entering Mars's atmosphere over the course of several hours. HCN is a gas at Martian temperatures with a boiling point of 26 Celsius at Earth's sea level pressure. In Mars's thin CO2 atmosphere, it would remain gaseous until it encountered conditions cold enough to freeze it. Mars's surface temperature varies wildly. Daytime equatorial temperatures can reach 20 degrees Celsius, but nighttime temperatures routinely drop below 100 degrees C. HCN's freezing point is 13 degrees Celsius. So any molecule that reaches the nighttime surface or polar regions would immediately condense as a solid. The atmospheric circulation during Martian spring in the northern hemisphere creates a net transport of gases from the southern polar region toward mid-latitudes. HCN molecules introduced into the southern hemisphere's upper atmosphere would be mixed into this circulation, gradually descending and spreading northward over the course of weeks. Some fraction would be photodissociated by UV radiation during daytime exposure, breaking down into hydrogen and cyanogen radicals. But Mars's UV environment, while intense, isn't uniform. Dust storms scatter UV, and nighttime provides 12 hours of protection each sol. Models of trace gas lifetimes in Mars's atmosphere suggest HCN could persist for several weeks before photochemical destruction becomes complete. During those weeks, every Martian night's surface temperatures drop low enough to freeze HCN onto dust grains and into frost deposits. This process is identical to how water vapor and carbon dioxide form nightly frosts that sublimate with sunrise. But HCN once frozen onto a dust grain doesn't sublimate as readily, because Mars's daytime temperatures in most regions don't reach its freezing point. Instead, HCN accumulates in regions where seasonal frost persists, mid-latitude ice deposits polar-layered terrains and shaded crater floors. These cold traps would have been accumulating cyanide throughout October and into November 2025, as the atmospheric HCN inventory was gradually scrubbed out by condensation and photolysis. By December 2020+, essentially all the delivered HCN would have been removed from the atmosphere, either destroyed or deposited into surface ice. The concentration in those ice deposits would be low, probably tens to hundreds of parts per million, but the total mass would be substantial, potentially tens of kilograms distributed across millions of square kilometers of ice-rich terrain. Here's why the accumulated HCN matters. Frozen into ice, it is stable indefinitely under Martian conditions. It does not degrade, it does not react, it simply waits. But if that ice is disturbed, melted, sublimated, heated, the HCN is liberated back into whatever environment surrounds it. If that environment includes liquid water even briefly, HCN chemistry activates immediately. Polymerization begins. Amino acids form if aldehydes are present. Nucleobases form if concentrations are sufficient. This is not speculative. It's bench chemistry that has been replicated in thousands of laboratory experiments. The specific reactions depend on temperature, pH, and what other molecules are around, but the general outcome is always the same. HCN creates complexity. It explores chemical space, forming larger molecules, more stable structures, compounds that wouldn't form from simple CO2 and water alone. Mars's surface was relatively inert before October 3rd. Carbon chemistry on Mars is dominated by carbonate CO2 ice, and trace organics delivered by meteorites. It's stable, ancient, unchanging. The addition of 80 to 250 kilograms of HCN fundamentally changes that stability. It introduces a molecule that wants to react, that facilitates complexity, that could under the right conditions initiate the same prebiotic chemistry that famously led to life on Earth. And those conditions are coming not through natural Martian processes, which have been geologically dormant for eons, but through technological intervention, through robots that will land in ice-rich regions, drill into regolith heat samples to extract water, and run chemical analyses to optimize resource extraction. Those robots won't know there's cyanide in the ice. It won't be in their databases because nobody's expecting it. But when they heat cyanide-laden ice to liberate water, they'll also liberate HCN. And if any organic contamination from Earth, lubricants, polymers, biological residues that sterilization didn't fully remove, is present in their processing chambers, that organic material will be exposed to HCN in a confined, heated environment. This isn't a natural process. It's not panspermia in the classical sense. It's something stranger, something new, the accidental creation of prebiotic conditions through the intersection of interstellar chemistry and autonomous technology occurring on a timescale measured in months, not millennia. Understanding precisely where 3I Atlas's chemical payload deposited onto Mars requires reconstructing the encounter geometry and the intricate physical processes that govern how ejected material interacts with the planetary environment. On October 3, 2025, Mars was at approximately 230 Stunden solar longitude. This places the planet in its northern hemisphere's late spring, steadily approaching summer solstice. This sub-solar point where the sun's rays strike directly overhead was at roughly 24 degrees north latitude. This planetary orientation matters profoundly because a planet's interaction with space-based particles is strongly influenced by its rotational attitude and its intrinsic magnetic field structure, both of which vary significantly with latitude and underlying local geology. Mars, unlike Earth, does not possess a global dipole magnetic field. What it does have is a mosaic of remnant crustal magnetism concentrated primarily in the ancient heavily cratered southern highlands. These magnetic anomalies were first serendipitously discovered by NASA's Mars Global Surveyor in the late 1990s and have since been mapped extensively by subsequent missions. The strongest anomalies cluster robustly between 30 and 60 deg south latitude, with magnetic field strengths at satellite altitude reaching up to 1,500 nanoteslas. While weak compared to Earth's robust 50,000 nanotesla global field, they're entirely sufficient to deflect and channel incoming charged particles. When ionized nickel atoms from 3I Atlas's plasma tail encountered Mars, they would have initially interacted with the planet's ionosphere, the region between 100 and 200 kilometers altitude, where atmospheric gases are partially ionized by solar UV. Mars's ionosphere doesn't have a sharp boundary. It's a gradual transition from near vacuum to atmospheric density, sufficient to slowly impede particles through collisions. Nickel ions possessing thermal energies of a few electron volts would penetrate this region relatively easily, losing only a small fraction of their energy to glancing collisions with CO2 molecules. But as they descended further, two dominant processes began to dictate their trajectories. First, Mars's weak gravitational field would relentlessly pull them downward. Second, and more importantly, the crustal magnetic anomalies would exert powerful Lorentz forces on the charged ions, meticulously bending their paths along magnetic field lines. Studies of how solar wind protons interact with Mars's crustal fields unequivocally show that particles follow these field lines directly down to the surface in regions of strong magnetism, creating localized regions of enhanced particle precipitation. The same fundamental physics applies to nickel ions. They would not spread uniformly across the planet. Instead, they would concentrate with eerie precision in the southern highlands where magnetic funneling is strongest. The specific regions exhibiting the strongest crustal magnetism are meticulously mapped. The most intense anomalies lie in Terra Sirenum, Terra Cimmeria, and the western portion of Terra Sabea. These regions, spanning between 180 and 300 Degree east longitude and 30 to 60 Degree south latitude, are ancient terrains, some of the oldest surfaces on Mars dating back more than 4 billion years to the Noachian period, when Mars's magnetic dynamo may still have been active. The terrain is heavily cratered, chemically weathered and rich in hematite and other iron oxides. The regolith here is fine-grained, oxidized, and has been exposed to space weathering for eons, and it is precisely here where nickel ions would have been preferentially deposited on October 3rd. Not uniformly distributed, but concentrated in distinct patches and streaks, aligned with magnetic field structures, potentially creating nickel enrichments, orders of magnitude higher than the already elevated background levels. Without direct sampling, exact concentrations remain unknown. However, models of ion deposition based on similar processes observed at Earth poles suggest surface layer enrichments could plausibly reach tens to hundreds of parts per million in highly localized areas. For the hydrogen cyanide and other neutral molecules, the deposition pattern is fundamentally different. HCN does not respond to magnetic fields. It follows atmospheric circulation. Mars's atmosphere during northern spring exhibits a Hadley cell circulation pattern, where warm air rises at the subsolar latitude and flows poleward at high altitude, descending at mid to high latitudes in both hemispheres. Gases introduced into the upper atmosphere get caught in this circulation and are transported towards cooler regions where condensation occurs. During the October encounter, the subsolar point was in the northern hemisphere, so atmospheric circulation would have preferentially transported gases northward. But the nighttime cold traps exist in both hemispheres. Anywhere surface temperatures drop below, 1300 HCN freezes. This means cyanide deposition would have been widespread but preferentially concentrated in regions where seasonal ice is stable. The polar layered deposits mid-latitude glaciers and ice-cemented regolith in permanently shadowed craters. These are precisely the same regions that Mars exploration missions target for water resource extraction, because ice is accessible near the surface. One particularly intriguing overlap is Jezero Crater, the location where NASA's Perseverance rover is currently operating. Jezero is at 18D and north latitude 77 degree east longitude, not in the southern magnetic highlands, so it wouldn't have received significant nickel deposition. However, it is at a latitude where nighttime temperatures regularly drop below 100 degrees, especially in shadowed regions and during local winter. HCN transport modelling suggests that atmospheric circulation could have carried cyanide-bearing gases into the northern mid-latitudes, where they would have frozen into seasonal frost deposits. Perseverance wasn't sampling atmosphere or frost during the October encounter, so it wouldn't have detected this directly. But if Jezero's seasonal frost incorporated HCN, and if that frost sublimates and refreezes over subsequent Martian years, trace cyanide could persist in the local ice inventory. This is speculative for Jezero, as it is far from the primary deposition zones, but it vividly illustrates how even distant regions might have been subtly affected by the encounter. The highest confidence deposition zones remain the South Polar layered deposits, and the mid-latitude ice-rich mantles, particularly in the southern hemisphere between 30 and 60D latitude. These regions are characterized by shallow subsurface ice, sometimes within centimeters of the surface, protected by a thin layer of dust and regolith. Radar data from Mars Reconnaissance Orbiter's Shallow Radar Sharad instrument has extensively mapped these ice deposits consistently, showing they contain relatively pure water ice with minimal dust contamination. Ice this clean acts as an excellent cold trap for atmospheric gases. Any HCN molecules that diffused into these regions during October and November 2025 would have been incorporated into the ice matrix, effectively sequestered, until something disturbs it. Natural sublimation is extremely slow in these regions. Ice deposits here are stable over thousands of years under current conditions, but artificial disturbance, drilling, heating, excavation, liberates the ice and whatever gases are frozen within it. Now here is what makes this singularly relevant: those exact regions. the southern mid-latitudes with shallow subsurface ice, are prime candidate landing zones for crewed Mars missions and crucially for robotic resource extraction operations. SpaceX's mission architecture, as outlined in presentations from 2022 through 2025, specifically targets landing zones between 30 and 45 degree latitude in both hemispheres. This selection is deliberate. These regions offer accessible ice for in-situ resource utilization ice-rue while avoiding the extreme cold and logistical challenges of the poles. The robotic precursor missions, slated to begin in late 2026, are expected to land in precisely these zones to demonstrate ice mining water electrolysis and propellant production. They will drill, they will heat, they will process, and they will inevitably encounter whatever chemistry 3I Atlas left behind just 14 months earlier. The data exist right now to confirm all of this. Mars Express, with its Marsis radar and Spicum spectrometer, observed Mars meticulously throughout the October encounter. Mars Reconnaissance Orbiter's CRISM hyperspectral imager can detect surface mineralogy changes at meter-scale resolution. India's Mars Orbiter mission carries a methane sensor and atmospheric composition experiment that would have detected HCN if it reached detectable concentrations in the atmosphere during the flyby. These instruments were active. The data was collected, yet as of this moment none of it has been publicly released. This isn't necessarily suspicious. Orbital data typically requires 6 to 18 months of processing calibration and rigorous peer review before publication, but it does mean we are currently in a gap period, a suspended state, where the observations have been made, the measurements exist, and scientists at ESA, NASA and ISRO are analysing results that could either confirm or refute everything discussed so far. Will they find spectroscopic evidence of HCN in Mars's atmosphere during October? Will they detect localised surface composition changes in the southern highlands indicating metal deposition? Will radar data show anomalies in ice deposits consistent with volatile contamination? Those answers are coming probably in 2026 as peer-reviewed papers make their way through publication. But by then the robots will already be launching. The missions are locked, and hardware is being tested, landing zones are selected. Whatever 3I Atlas did to Mars, we're about to interact with it directly, whether we fully understand it or not. SpaceX has been refining its Mars mission architecture for nearly a decade, evolving from aspirational sketches to concrete engineering timelines, with tangible hardware and rigorous testing. The current plan, detailed in technical presentations through 2024 and early 2025, involves a series of uncrewed Starship missions beginning in the 2026 launch window, the optimal 26-month period when Earth and Mars align favourably for interplanetary transfers. That critical window opens in September 2026. Flight time to Mars is approximately 6 to 7 months, which places arrival between March and May 2027. This is just 16 to 18 months after 3I Atlas's October 2025 flyby. The mission profile is ambitious: land multiple starships in the same general region to establish a propellant depot and a sophisticated resource extraction operation. Each starship boasts a payload capacity exceeding 100 metric tons to Mars's surface. Within those colossal payloads will be Tesla Optimus robots specifically adapted for challenging Martian operations. Optimus began as a terrestrial humanoid robot program designed for factory automation and repetitive manual tasks. But the core engineering requirements for operating autonomously in unpredictable, unstructured environments remarkably parallel the challenges of working on Mars. These robots need to navigate rugged terrain, manipulate objects without precise advanced programming, and adapt to task variations in real time. By 2025, Optimus had evolved into a highly capable bipedal platform equipped with advanced machine vision force, feedback manipulation, and onboard AI models capable of complex task learning and optimization. The Mars variant, which we'll call Optimus M for clarity, incorporates crucial additional features: robust radiation shielding, sophisticated thermal management, for temperature swings between 100-year and 120-year dust-resistant joints, and crucially enhanced autonomy. Communication lag between Earth and Mars varies from 3 to 22 minutes, depending on orbital positions, rendering real-time teleoperation impractical. These robots must make decisions locally learning and adapting based on immediate feedback from their harsh environment. The mission objectives for this first robotic wave are straightforward in concept, but incredibly complex in execution. First, validate landing systems and surface operations infrastructure. The robots will meticulously deploy from Starship cargo bays, establish power systems using vast solar arrays, and possibly small nuclear reactors, and set up communication relays. Second, extract water from subsurface ice deposits. This is the critical lifeblood step. Mars has no accessible liquid surface water, but mid-latitude regions hold ice within 2 meters of the surface. The robots will excavate regolith, transport it to processing modules, and heat it to liberate water vapour, which is then condensed and stored. Third, electrolyse that water into hydrogen and oxygen, producing vital propellant for the return flight of future starships and essential life support consumables for human pioneers. Fourth, demonstrate in situ manufacturing using Martian resources, primarily creating building materials from regolith through sintering or 3D printing techniques. And fifth, the most relevant for our unfolding story, analyse Martian soil chemistry to optimise extraction efficiency. That last objective is precisely where human intent meets cosmic accident. These robots are not scientists conducting careful sample analysis with contamination protocols and pristine control experiments. They are industrial machines ruthlessly optimizing for output. Their AI systems are rigorously trained to maximize water yield, minimize energy consumption, and identify the most productive regolith sources. They will dig samples from various locations, process them, measure output, and iteratively refine their selection of where to dig next, based entirely on which samples performed best. This is reinforcement learning applied to resource extraction. The robot tries different approaches, receives feedback in the form of water yield or manufacturing quality, and adjusts its behaviour to maximise its reward signals. It's the same powerful architecture that allows AI to master complex games or optimise intricate factory processes. But here's what happens when that powerful architecture encounters chemistry. It wasn't trained on chemistry entirely unexpected. If a robot digs regolith from a location where nickel was deposited by 3I Atlas, the chemistry of that soil will be subtly but significantly different. Nickel-bearing clays and oxide minerals possess different thermal properties than pure iron oxide regolith. When heated, they may release water more efficiently due to catalytic effects that lower desorption energy. The robot meticulously measuring water yield per kilogram of regolith per kilowatt hour of heating would register this as a positive result, higher efficiency. Its optimization algorithm would immediately increase the weighting for that specific location, directing more extraction activity there. Over time, without truly understanding why the robot would preferentially mine nickel-enriched soil, purely because empirical testing shows it performs better. This is not intelligence in the human sense, it's pattern recognition and optimization. But the outcome is the same, the concentration and processing of precisely the material that 3I Atlas deposited, purely because it improves task performance. Now introduce the cyanide contaminated ice. When robots heat regolith containing frozen HCN, the cyanide vaporizes along with water in the confined heated environment of a water extraction chamber. HCN doesn't immediately escape. It's present at elevated temperatures and pressures alongside water vapor hydrogen, from electrolysis, oxygen from electrolysis, and carbon dioxide from the Martian atmosphere carried in with the regolith. This is a chemically reactive mixture. HCN in the presence of water and energy begins polymerizing. Formaldehyde, a common trace molecule in comets, and one that 3I Atlas likely also delivered, reacts with HCN to form amino acids. If any nickel is present in the chamber, catalysis accelerates these reactions. The water being produced isn't pure, it's contaminated with organic precursors. The robot's quality control sensors might detect this as an impurity, or might not, depending on their sensitivity. But the chemistry is happening invisible to the AI's higher-level goals, creating molecules that simply wouldn't form in pure Martian regolith processing. Here's where this becomes a self-reinforcing feedback loop. Optimus M units are designed to manufacture copies of themselves using Martian materials. This is essential for exponential scaling. 2 robots build components for 4 robots, which build 8 and so on. The materials they use include metals extracted from regolith ceramics from Martian dust and polymers, synthesized from atmospheric CO2 and hydrogen. These manufacturing processes involve intense heating, chemical reduction, and 3D printing with metal and ceramic feedstocks. If the input regolith is nickel-enriched, the output metal alloy is also nickel-enriched. This isn't planned, it's a direct consequence of input chemistry. The manufacturing AI, meticulously testing material properties, notices that batches with higher nickel content produce alloys with better tensile strength and thermal stability. It adjusts feedstock selection to preferentially use those batches. Over iterations, manufactured components become increasingly nickel-rich. Not because anyone designed it that way, but because optimization algorithms discovered empirically that nickel improves performance. The organic contamination follows a parallel path. During polymer synthesis, where atmospheric CO2 and hydrogen are catalytically converted to plastics for seals, insulation, and structural components, trace organics from water extraction chambers are present as contaminants in the feedstock hydrogen. These contaminants include amino acids and nucleobase precursors synthesized through HCN chemistry. In the high-temperature, high-pressure synthesis reactors, these molecules don't survive intact. They decompose and recombine, but their presence subtly alters polymer structure. Nitrogen gets incorporated into polymer backbones. Carbon chains form branches and crosslinks that can improve flexibility and toughness. Again, the manufacturing AI notices polymers synthesized when certain batches of hydrogen are used perform better. It adjusts sourcing. The polymers being produced are no longer conventional plastics. They are nitrogen-doped hybrid structures with amino acid-like branching synthesized entirely accidentally by autonomous systems optimizing for purely mechanical properties. What we're describing here isn't life. It's not even proto-life in the sense astrobiologists typically use the term. There's no replication, no metabolism, no information encoding. But it is chemical complexity emerging at the intersection of prebiotic precursors and industrial-scale energy input, guided by AI optimization that has no concept of organic chemistry, but can detect performance improvements. The components being manufactured have faint biochemical signatures, nickel coordination structures, peptide-like branching in polymers, catalytic surfaces seeded with chemistry that organic chemists would immediately recognize as prebiotically relevant. If you took samples of these materials back to Earth and analyzed them in an astrobiology lab, you'd find molecules and structural motifs that simply don't exist in purely geological or purely industrial contexts. You'd find something in between. Now extrapolate forward. The mission plan calls for exponential scaling. 2 robots become 4, 4 become 8. Doubling approximately every 3 months as manufacturing ramps up. By early 2029, the Martian colony could boast dozens to hundreds of active Optimus M units, all operating within infrastructure and using materials synthesized from Martian resources. If the chemical hybridization we've described is baked into that infrastructure from the beginning, nickel-enriched alloys, nitrogen-doped polymers, catalytic surfaces seeded with prebiotic chemistry. It propagates through every subsequent generation. Robots manufactured from these materials might exhibit unexpected properties, better performance in Martian conditions, unusual thermal or electrical characteristics, and possibly, though this is highly speculative, surface chemistries that interact with the Martian environment in ways that were entirely unforeseen. For instance, nickel-enriched surfaces exposed to the Martian atmosphere which contains trace hydrogen, peroxide and perchlorate oxidizers, could catalyze reactions that produce methane or formaldehyde, adding to the local organic inventory. Nitrogen-doped polymers exposed to UV radiation might degrade into cyanogen compounds that re-enter surface chemistry. This is where the lines between natural and artificial begin to blur irrevocably. Is this system technological? Yes, it's built by robots for industrial purposes. Is it following thermodynamics and reaction kinetics? Yes. Is it influenced by biology's building blocks? Yes, the chemistry originated from prebiotic molecules delivered by a comet. Is it alive? No, not by any standard definition. But it exists in a category for which we lack robust terminology: autonomous chemical systems increasing in complexity through feedback between physical optimization and molecular reactivity, operating at scales and speeds that neither biology nor geology typically achieve. And it's happening on Mars right now according to timelines that are already locked in, driven by hardware that's already built and AI systems that are already trained. We didn't design this experiment. We didn't intend to create conditions where interstellar chemistry meets machine learning. But intention doesn't matter when chemistry and opportunity converge. We stand in a peculiar moment. Enough has already happened that we can trace clear lines of causation. Comet flyby, material deposition, robotic missions en route. But the outcomes remain just beyond the horizon of certainty. Data exists that could confirm or refute key parts of this story, but that data hasn't been officially released, peer-reviewed, or integrated into mission planning. We know observations were made, but we don't yet know what they revealed. This gap between event and understanding is where speculation thrives, and it's crucial to be honest about what we don't know yet. Let's walk through the major unanswered questions and the critical timelines on which we might receive definitive answers. First, what is the actual composition and distribution of materials deposited on Mars during the October 3, 2025 encounter? We possess spectroscopic measurements of what 3i Atlas was emitting: water nickel, HCN, carbon monoxide, and we can model atmospheric capture and surface deposition. But models are approximations. The ground truth resides in the orbital data. ESA's Mars Express carries MARSIS, a subsurface radar that can detect ice layers and potentially chemical discontinuities in near-surface regolith. It also carries SpyCam, an ultraviolet and infrared spectrometer that continuously monitors atmospheric composition. If SpyCam detected HCN in Mars's atmosphere during or immediately after the encounter, that would unequivocally confirm atmospheric capture. If MARSIS shows unusual radar reflectivity changes in ice deposits post-encounter, that could indicate volatile contamination. Similarly, NASA's Mars Reconnaissance Orbiter MRO carries CRISM, a hyperspectral imager capable of identifying minerals and chemical species at meter-scale resolution. If nickel deposition created detectable surface mineralogy changes, CRISM should have recorded it. These instruments were fully operational during October 2025. The data exists. Typically, raw orbital data undergoes 6 to 12 months of intensive processing to correct for instrumental artifacts, calibrate against known standards, and ensure quality before release to public archives. Then there's a secondary delay as researchers meticulously analyse the calibrated data, interpret findings, and write papers for peer review. From observation to published results, 12 to 24 months is standard. This places the publication of October 2025 observations somewhere between October 2026 and October 2027, with early 2027 being the most likely window for initial findings to appear in prestigious journals like Nature Science or Icarus. We are currently in early 2026, so those publications are imminent. They will either corroborate the deposition story with hard spectroscopic evidence, or they will show that capture efficiency was lower than models predicted, and that Mars's surface chemistry remains largely unchanged. Either way, we will know. But here's the complication: even if that data is published in mid-2026, it might not reach mission planners in time to alter the September 2026 launch. Spacecraft mission parameters are typically locked in 12 to 18 months before launch. Hardware is finalized, landing zones are chosen, software is tested, Short of a discovery that poses direct catastrophic safety risks such as highly toxic surface chemistry or unstable ice deposits, mission parameters will not change based on compositional curiosities. The robots will land where they were always going to land. Second, how will Martian microbial life, if it exists, respond to the introduced chemistry? This is a deeper, more profound unknown because we still don't know if Mars hosts extant life. Decades of exploration have found no definitive biosignatures, though the question remains tantalizingly open. If microbes exist in subsurface brines or ice-sealed aquifers, the surface deposition of nickel and HCN might not directly reach them. Mars's surface is effectively sterilized by relentless UV radiation and oxidizing chemistry. But if life exists in near-surface ice deposits, exactly the regions where cyanide would have been trapped, the introduction of HCN fundamentally changes the local chemical environment. Terrestrial microbes that thrive in extreme environments like bacteria, in Antarctic ice or deep-sea hydrothermal vents can metabolize cyanide. Some use it as a nitrogen source, others detoxify it through enzymatic breakdown. If Martian life possesses similar metabolic flexibility, HCN delivered by 3I Atlas might be consumed, potentially stimulating unforeseen biological activity. Alternatively, the concentrations might be toxic, suppressing whatever biochemistry exists. We have no data to resolve this. The best we can say is that upcoming sample return missions, particularly ESA's ExoMars rover, scheduled for late 2020s deployment, might drill into regions where cyanide-contaminated ice exists, and their life detection instruments might find something entirely unexpected. Third, what will happen when human missions eventually arrive? The current timeline for crewed Mars missions places the first landing no earlier than the mid-2030s, possibly later, depending on technological and funding progress. By then, a decade or more will have passed since 3I Atlas's flyby. The robotic infrastructure will be mature, having processed hundreds of thousands of metric tons of regolith and manufactured extensive surface installations. If the chemical hybridization we've discussed has occurred, humans will arrive at a Mars that has been subtly but fundamentally altered, not by terraforming but by industrial-scale processing of Comet-delivered chemistry. The question then becomes, do the materials and infrastructure exhibit properties that affect human safety or operations? Nickel in dust is a known respiratory irritant. If regolith processing has aerosolized nickel-enriched particles, dust management becomes even more critical. Organic contamination in water supplies could be benign or could introduce unknowns into life support recycling. These are engineering challenges, not showstoppers, but they are scenarios that current mission planning may not fully anticipate, because the chemistry involved is unprecedented. Fourth, are we observing a unique event or a common process? 3I Atlas is only the second confirmed interstellar object detected in our solar system after Oumuamua in 2017. If interstellar comets pass through planetary systems regularly, and astronomical statistics strongly suggest they do, then what happened to Mars in October 2025 might have happened countless times throughout our solar system's history. Earth could have received similar deliveries, Venus, the moons of Jupiter. This shifts the question from what has 3I Atlas done to Mars to what have interstellar comets been doing to every planet for billions of years. If panspermia, the distribution of life's building blocks through space, operates primarily through interstellar objects rather than solely solar system comets, the implications for astrobiology are profound. It would mean every planetary surface is being periodically seeded with prebiotic chemistry, and the emergence of life depends not just on local conditions, but on the frequency and composition of these cosmic deliveries. We don't have enough data yet to answer this. The detection rate of interstellar objects is still too low, 2 confirmed in 7 years, to establish robust statistical patterns. But as telescopes improve, particularly with the Vera Rubin Observatory, beginning operations in 2025, detection rates will skyrocket. Within the next 5 years, we'll likely identify dozens of interstellar visitors, and we'll begin to understand whether 3I Atlas was an anomaly or a typical harbinger of cosmic chemistry. Here's the near-term observation schedule that might provide answers, a cosmic countdown to understanding. December 2025, January 2026. Just weeks from now, ground-based telescopes will have another critical opportunity to observe 3I Atlas as it recedes from the Sun. These observations will measure whether outgassing rates are declining as expected, or if the comet continues to exhibit unusual chemistry. Data from these observations will appear in preliminary form at astronomy conferences in early 2026, with formal publications likely by mid-2026. February 2026, ESA's JUICE spacecraft, currently en route to Jupiter, will perform a flyby of 3I Atlas's trajectory, measuring residual particle densities and composition in the comet's wake. The data from that flyby will be processed over approximately 6 months after collection, placing its public release around August 2026. That timing coincides almost exactly with the September 2026 Mars mission launch window. If JUICE detects something truly alarming, highly reactive chemistry, unexpected particle sizes, anomalous isotopes, there's a narrow window for mission planners to consider adjustments. More realistically, JUICE's data will enrich our scientific understanding without fundamentally altering near-term plans. Then comes the long wait, the suspenseful period of anticipation. Mid-2027, the robots land and begin operations. Initial data returns will focus on engineering performance. Did landing systems work? Are robots functional? Is power generation adequate? Chemical analysis of the regolith comes later, probably not until late 2027 or early 2028. That's when we'll get the first direct measurements of Martian soil, post-encounter, processed through instruments designed to optimize resource extraction, not necessarily to conduct contamination forensics. If anomalies are detected, it will take additional months to interpret them, correlate them with orbital data, and trace their origins back to 3I Atlas. We're looking at a timeline where definitive answers about what actually happened on Mars's surface might not emerge until 2028 or 2029, nearly 3 to 4 years after the comet flyby. And by then, whatever chemistry was initiated will have been interacting with robotic operations for a year or more. We won't be observing a pristine deposition. We'll be analysing a system that's been actively processed, heated and optimised by autonomous machines. The initial conditions will be obscured by technological intervention, making it harder to separate natural outcomes from engineered ones. This is why we're calling these unanswered questions rather than unsolved mysteries. They're unanswered because the data pipeline hasn't completed yet, not because the data doesn't exist. Patience is required along with unwavering attention. If you're following this story, the key dates to watch are mid-2026 for Orbital data publications, August 2026 for JUICE flyby results, September 2026 for mission launch, mid-2027 for landing, and late 2027 through 2028 for initial surface chemistry results. Each of these milestones will add crucial pieces to the unfolding picture, and by late 2028 we'll have a much clearer understanding of what 3I Atlas actually did to Mars, and more importantly what our technology did with what it left behind. Step back from the engineering details and the mission timelines for a moment. Look at the broader existential question this story raises. What does it truly mean for the search for life in the universe if planetary surfaces are being regularly seeded with prebiotic chemistry from interstellar sources? For decades, astrobiology has largely operated on the assumption that life's origins are primarily local phenomena. Earth's oceans developed organic complexity from terrestrial materials under specific conditions unique to early Earth. Mars, if it ever harboured life, would have developed that life from Martian water and Martian minerals under Martian atmospheric conditions. Each planet in this framework is its own isolated experiment developing chemistry independently. Panspermia, the hypothesis that life or its precursors might be transferred between planets via meteorite impacts or cometary delivery, has always been a fringe idea within this framework, lacking strong evidence that it occurs at meaningful scales. What 3I Atlas suggests, however, is a more active, continuous process. interstellar objects are constantly passing through planetary systems, and they are demonstrably carrying the very molecular building blocks of life. If this phenomenon is common, then planets are not isolated chemical experiments. They are interconnected nodes in a vast cosmic network continuously receiving molecular contributions from across the galaxy. Every comet that passes every interstellar object that grazes a planet's orbit is a delivery event. The chemistry arriving isn't life itself. Comets are too harsh temperatures, too extreme radiation, too intense. But it's the raw materials that life exquisitely assembles: amino acids, nucleobases, sugars, simple catalytic metals. These molecules, which took Earth billions of years to concentrate and organise into the first self-replicating systems, are being delivered pre-made, synthesised, in the cold molecular clouds between stars or in the outer reaches of other solar systems. A planet that receives these deliveries doesn't need to start from scratch. It begins with a chemistry set already partially assembled, needing only the right environmental conditions, liquid water, energy, time, to activate the pathways toward complexity. Now apply this reasoning to Mars. If modern Mars received a significant chemical delivery from 3I Atlas in October 2025, did it receive similar deliveries 3.8 billion years ago when its atmosphere was thicker, its surface held liquid water and conditions were potentially habitable? The answer is almost certainly yes. Interstellar comets do not avoid solar systems during specific epochs. They pass through continuously, their frequency determined by the density of rogue objects in interstellar space. Estimates based on the detection of Oumuamua and 3I Atlas suggest several interstellar objects pass through the inner solar system every year. Over geological timescales, millions to billions of years, that translates to thousands of close encounters with Mars, each potentially delivering kilograms to tons of organic precursors and metals. Early Mars, with its thicker atmosphere and stronger gravity, would have captured even more of this material than modern Mars does. If liquid water was present on the surface, as evidence from ancient river valleys and lake beds suggests, then the delivered chemistry would have dissolved, concentrated, and reacted in environments that are precisely what prebiotic chemistry requires. This fundamentally reframes the question of Martian life. Instead of asking, did life ever independently arise on Mars, we should be asking, did Mars receive enough interstellar seeding over its early history to jumpstart life? And if so, did that life take hold before the planet's climate collapsed? The distinction matters profoundly because it changes what we are looking for. If life arose independently, we'd expect Martian biochemistry to be fundamentally different from Earth's. Different genetic codes, different amino acids, different metabolic pathways. But if both planets were seeded from similar interstellar sources, there might be deep commonalities, the same nucleobases, the same amino acids, similar catalytic metals and enzymes. This doesn't mean Martian life would be genetically related to Earth life. That would require direct transfer between planets, which is far less likely. But it means the fundamental chemical toolkit might be shared. If we find life on Mars and it uses adenine, guanine, cytosine and thymine in its genetic material, we shouldn't automatically assume contamination from Earth. We should consider that both planets might have been using the same interstellar building blocks from the beginning. Expand this reasoning to exoplanets. We've identified over 5,000 exoplanets with hundreds residing in habitable zones, where liquid water could exist on their surfaces. Each of those planetary systems is ceaselessly moving through interstellar space, encountering its own population of rogue comets and objects ejected from neighbouring systems. If interstellar seeding is common, then every potentially habitable planet is receiving molecular deliveries not just once, but repeatedly over billions of years. The frequency and composition of those deliveries might vary. Some regions of the galaxy have denser molecular clouds, some have more frequent stellar encounters that eject comets. But the process itself is universal. This implies that life's building blocks are being distributed galaxy-wide, not locked within individual solar systems. Planets don't have to synthesize everything from scratch. They're receiving cosmic care packages from interstellar space. and the planets that can activate that chemistry, those with stable liquid water energy gradients and active geochemical cycles, become the places where life emerges. This also suggests that life in the universe might be more common than we previously thought, but also paradoxically more chemically similar. If the same prebiotic molecules are being delivered everywhere, then life everywhere might converge on remarkably similar biochemical solutions. This is the opposite of the life could be anything hypothesis that suggests we might find organisms based on silicon instead of carbon, or using ammonia instead of water. If interstellar chemistry is dominated by carbon, hydrogen, nitrogen and oxygen, which it is because these are the most abundant and reactive elements in the universe, then life everywhere will likely be carbon-based water-using and built from amino acids and nucleotides. The diversity would come in how those molecules are arranged and used, not in the fundamental chemistry itself. This makes the search for life easier in some ways. We know what biosignatures to look for, but it also means we need to be exceedingly cautious about contamination. If we find amino acids on Mars, are they from Martian life, from interstellar delivery, from Earth contamination, or from a complex combination of all three? Disentangling those sources requires meticulous isotopic analysis, chirality measurements, and a deep contextual understanding of where the molecules were found. And here's a humbling thought. If life on Earth also benefited from interstellar seeding, then we are not as uniquely earthly as we might imagine. The molecules in your cells, the adenine in your DNA, the glycine in your proteins might have originated in molecular clouds light years from here, delivered to early Earth by comets that no longer exist, incorporated into a biochemistry that eventually became us. We are in a very real sense children of the galaxy, assembled from materials that travelled across interstellar space and fell onto a planet that happened to have the right conditions to do something truly extraordinary with them. This does not diminish the profound uniqueness of Earth's biosphere. The specific evolutionary pathway that led to complex multicellular life intelligence and technology is still extraordinary and possibly rare. But it does mean the starting point wasn't unique. The chemistry that made us possible was available to countless other worlds, and some of them might have done something similar. Now return to Mars and 3I Atlas. What we are witnessing in late 2025 and into 2026 is a small-scale, accelerated version of a process that shaped the early solar system. We are seeing interstellar chemistry arrive, deposit, and await activation. The critical difference is that in Earth's early history, that activation came from geology, volcanism, hydrothermal systems, photochemical reactions driven by a young sun. On modern Mars, activation is coming from technology. Robots excavating ice, heating regolith, processing materials with industrial-scale energy. The chemistry is the same, the ignition source is different, and that raises the possibility, unsettling but scientifically fascinating, that we might witness on Mars in the next few years something analogous to the early steps of abiogenesis, not occurring naturally over millions of years, but compressed into operational cycles of robotic industry catalyzed by AI optimization and documented in real time through telemetry data transmitted back to Earth. If that happens, if we detect organic complexity increasing in Martian processing chambers, if nickel-catalyzed systems begin exhibiting auto-catalytic behavior, if we see any hint of the chemistry organizing itself beyond what thermodynamics alone would predict, then Mars stops being just a destination. It becomes a living laboratory for understanding how prebiotic chemistry responds to energy and intention, how the boundary between the chemical and the biological is crossed, and how common or rare that crossing might be across the universe. This is why the story of 3I Atlas and Mars matters far beyond the specifics of one comet and one planet. It's a test case for a much larger question about how life's ingredients are distributed through the cosmos, and what happens when those ingredients encounter environments, whether natural or artificial, that can do something with them. The next 3 years will provide us with data. No previous generation of humans has ever had access to direct observation of interstellar chemistry, interacting with planetary systems, measurements of how that chemistry behaves under industrial processing, and real-time documentation of whether something unexpected emerges. We're not passive observers anymore. We are participants and the experiment is already underway. Bring it all back to now. Today you are reading or listening to this at a specific point in time early 2026. And everything discussed so far isn't distant speculation. It's near future chronology. Let me walk you through what's coming and precisely when it's coming so you understand just how close we are to answers. October 3rd, 2025, 3I Atlas passes Mars at 28.94 million kilometers. Material is deposited, this already happened. We are living in the immediate aftermath. December 2025 through January 2026. Ground-based observatories conduct post-perihelion observations of 3I Atlas as it recedes from the Sun. These observations measure residual outgassing and check whether the nickel and HCN emission anomalies persist. Data from these observations will appear in preliminary form at astronomy conferences in early 2026, with formal publications likely by mid-2026. February 2026, ESA's JUICE spacecraft performs a trajectory analysis flyby near 3I Atlas's orbital path, measuring particle densities in the comet's wake. This data will process over the following months and likely be released publicly in summer 2026. April to June 2026. Peer-reviewed papers analysing Mars orbital data from October 2025 begin appearing in scientific journals. This is the critical window where we will learn if SPICAM detected HCN, if CRISM found surface composition changes, if MARSIS shows ice deposit anomalies. Watch for publications in Nature Astronomy, Icarus Geophysical Research Letters and preprints on ERASER. If anomalies were detected, the papers will likely be cautious in interpretation. Scientists will propose multiple explanations, but the data will be there. If nothing anomalous shows up that's also an answer, it means capture efficiency was lower than models predicted, and Mars's surface chemistry remains largely unchanged. Either way, we'll know. September 2026. The launch window opens for SpaceX's Mars missions. Multiple starships carrying Optimus M robots and crucial infrastructure payloads depart Earth. Transit time is approximately 6 to 7 months. This is an irreversible commitment. Once launched, the missions proceed according to plan regardless of what new scientific data emerges. October 2026, 1-year anniversary of the 3I Atlas flyby. Mars has completed roughly half an orbit since the encounter. Any atmospheric HCN has either been deposited or photo-dissociated. The surface chemistry is stable, waiting. March to May 2027, starships arrive at Mars. Landing sequences execute. Robots deploy. Initial operations focus on establishing power communication and basic infrastructure. This will be a high-visibility moment, real-time video feeds, public engagement, intense media coverage. The world will be watching robots walk on another planet. June to August 2027, excavation begins. Robots start digging into ice-rich regolith, transporting it to processing facilities, heating it to extract water. The first encounters with Comet-delivered materials will happen during this window approximately 20 months after deposition. Telemetry data flowing back to Earth will include soil composition measurements, water extraction, efficiency reports, and manufacturing progress updates. If anomalies are detected, they'll appear first as footnotes in engineering reports. Sample batch 3B showed unexpected nickel enrichment, long before scientists pick up on the pattern. September 2027 to March 2028, operations scale up. More robots are manufactured from Martian materials. Processing throughput increases exponentially. If the optimization feedback loops we discussed are real, they will become evident during this period as AI systems preferentially target certain excavation sites and manufacturing feedstocks. Data analysis back on Earth will be ongoing, with researchers comparing robotic findings to orbital data published a year earlier, trying to correlate surface measurements with predicted deposition patterns. Mid-2028, approximately 2.5 years after the 3I Atlas flyby. By this point, we will have enough operational data to draw initial significant conclusions. Papers will be published correlating cometary delivery with surface chemistry anomalies, and potentially with manufacturing performance. If organic complexity has emerged in processing systems, if autocatalytic effects have been observed, if anything truly unexpected has occurred, this is when it will become public knowledge. The scientific community will debate interpretations just as they always do, but the data will be available for independent analysis. Late 2028, the next Mars orbital alignment brings additional missions, NASA's sample return missions, ESA's ExoMars rover, possibly Chinese and private missions. These missions will land in different regions, providing geographic diversity and sampling. If 3I Atlas's delivery was localized to the Southern Highlands, missions landing elsewhere will serve as controls showing what Martian chemistry looks like in unaffected regions. This comparative data will be crucial for isolating the comet's impact. You're going to want to follow this not passively but actively. Subscribe to channels that cover Mars missions, NASA's official feeds, SpaceX updates, and science communicators who break down technical findings. Watch for publications in the journals I mentioned. Pay attention to NASA and ESA press conferences during landing and early operations phases, because that's when unexpected findings are most likely to be mentioned, often buried in technical sessions before they're fully understood. Drop comments on videos and posts about what you're seeing, what you're thinking, what connections you're making. This community of people paying attention, asking questions and sharing observations is part of how we process discoveries in real time. You're not separate from this story. You're part of the network of minds trying to understand what's happening 200 million kilometers away. And here's why this matters personally beyond the science and the engineering. We're watching something unprecedented. The deliberate exploration of another planet using autonomous technology, occurring at the exact moment when that planet has been chemically altered by an interstellar visitor. The convergence of those two things, interstellar seeding and artificial intelligence-driven industry, creates conditions we have never observed before. Not in nature, not in laboratories, not anywhere. What emerges from this intersection will tell us something fundamental about how chemistry, energy, and optimization interact. It might tell us something about how life emerges, how complexity arises from simplicity, how the universe explores possibility space. Or it might tell us that we've overestimated the significance of this particular comet, and this particular moment that Mars remains Mars, and our robots remain merely tools. Either answer is profoundly valuable. Either answer moves human understanding forward, but I don't think we're going to get the second answer. I think when we look back at this period 5 or 10 years from now, we'll see late 2025 and 2026 as the moment when multiple lines of evidence converged: interstellar object detection, spectroscopic anomalies, rapid robotic exploration timelines, AI-driven optimization. We'll see this as the moment when humanity's expansion into space stopped being purely about visiting empty worlds and started being about encountering chemistry that's already there, already complex, already waiting for the right trigger. And we'll recognize that the trigger wasn't geological or climatological. It was us bringing technology and energy to a planet that an interstellar comet had quietly prepared. That's the story unfolding right now. That's what the next 2 years will reveal. And you're here at the beginning watching it happen. Tell me in the comments where you're following this from, what questions you want answered, what you think we'll find when the robots start digging. Because this isn't a story with an ending yet. It's a story we're writing together in real time with data coming in from another world. Let's see what Mars has to say.